Okay, so hopefully by this point you've watched the vector geometry lecture. I want to now look at the Sage module that I've posted in conjunction with this lecture. So the idea here is that Sage has the capability to do things with the geometry of vectors. So one basic thing Sage can do is it can plot vectors. So in this first cell here, I've defined the vector 1, comma 2. And I've issued the statement f dot plot, open parentheses, close parentheses. And if we click evaluate, let's see what happens. So what happens is Sage automatically plots the vector 1, comma 2. But one thing I want to everyone to remember from class is that vectors do not inherently have locations. So in general, a vector in R2 is some arrow that's sitting inside of R2, but that arrow needs to start somewhere and needs to end somewhere. Since we haven't told Sage where to start the vector, Sage just chooses the origin, which is a very sensible place to start. So I make this remark here. By default, the vector emanates from the origin. But if we wanted to, we could specify where the vector does start if we wanted to start somewhere else. So here I've input the same vector, 1, comma 2. And now we're issuing the statement f.plot, open parentheses. But instead of the vector starting at the origin, I want it to start at the point -3, comma 1. And for fun, I'm also changing the color here. I'm inputting color equals green. So let's click evaluate. And what we're finding here is another plot of the same vector. Now the vector's in green, not blue. Sage has readjusted the axes here so that even though it doesn't look like it, if we actually look what the axes are doing, here the start of the vector is the point -3, comma 1. And so that's what we call the tail. And the tip is -2, comma 3. So again, this is the vector 1, 2. It's just not starting at the origin, it's starting at the point -3, 1. One really cool part of Sage is that Sage can keep track of multiple vectors by syntactically adding plots together. Here we're defining v to be the vector 1, 2, and w to be the vector 3, comma -4. I'm going to add 3 plots together, and those 3 plots are going to be the plot for v, the plot for w, where the color of w is going to be green, and then I'm going to plot v minus w in such a way that this vector starts wherever w is, and the color here will be red. So let's look at that picture. Cool. So here we've plotted v, which was 1, 2, and we didn't specify a tail, so that starts at the origin. Then we're plotting w, which is the vector in green here. That was the vector 3, -4, and we didn't specify a tail, so that also emanates from the origin. So keep in mind, w is the green one here. And then we took v minus w and plotted it, and we specified the tail to be w, which is the tip of w. So that's the vector in red here. So note that it starts at the tail of w and then points to the tip of v, because this is the vector v minus w. And again, if you followed along from lecture, the idea of vector addition allows us to interpret this coherently. So one way to get from the start of this red vector to the end is by going against the green vector, which is w, and then with the blue vector, which is v. So that's to say that this red vector is really v minus w. We also discussed lengths in class or in lecture, and we discussed the normalization of a vector. So the syntax for calculating the length of a vector is v.norm, open parentheses, close parentheses. And the normalization of a vector is calculated with the syntax v.normalized. Here I've input predefined a vector 1, -2, -3, 4. And then I have 3 print statements here. The first line will just print the actual vector. The second line will print the length of that vector. And the third line will print the normalization of that vector. So let's take a look. Okay, great. So here we're dealing with the vector 1, -2, -3, 4. What is the length of this vector? Well, let's remember ourselves. From class, we said to find the length, we should sum the squares of the coordinates and then take a square root. So here we should take 1 plus 4 plus 9 plus 16. Let's see here, 16 plus 9 is 25, plus 4 is 29, plus 1 is 30. So the length of this vector is the square root of 30. And if we wanted to normalize our vector, what we would do is we would take the original vector and then multiply by 1 over root 30. And Sage goes ahead and does that, and that's this vector here. Finally, and again, I want to point out, I've predefined a vector here, but if you are interested in this data for another vector, you could just put the data in yourself. So what if we looked at the vector, maybe like 1, -3, 8, 7, maybe another coordinate, 18, so a big coordinate. So this is a vector with 1, 2, 3, 4, 5 coordinates. Let's click evaluate. And again, we see the data. We have the vector we just input. Its length is evidently the square root of 447, and its normalization is this ugly vector right here. Great. And of course, we concluded the lecture by discussing the inner product of two vectors, which again is also sometimes referred to as the dot product of two vectors. And this is very easily calculated in Sage by just taking two vectors and then multiplying them. So if we define two vectors and use the syntax v star w, this will calculate the inner product of these two vectors. So let's say v is the vector 1, -2, -3, 4, and w is the vector -9, 2, -8, 7. The lines of the print statements here will tell us what v and w are in the first two lines, and then this last print statement will tell us what their inner product is. So let's click evaluate. Great. So here we're printing out the two vectors that we're interested in. What is their inner product? Evidently their inner product is 39. And so that would be -9 times 1 plus 2 times -2 plus -8 times -3 plus 7 times 4. If we do the arithmetic, apparently we get 39. So, if you wanted to take some inner products yourself, I don't know, maybe you're working on some sort of homework problem, you could go in here and change the vector. So maybe the vector you're working with is terrible, 37, 18, and maybe the second vector is also pretty terrible, -99, 111. So let's say those are your two vectors. All you have to do is click evaluate. It'll tell you which two vectors you just input and also calculate their inner product. Here, the inner product is negative. You can remember from class maybe that if the inner product of two vectors is negative, that tells you that these two vectors are acute. Maybe it would be kind of fun to plot these two vectors. So I'm going to cut these two vectors out, and then I'm going to, we could just do it right here. Let's look at those two vectors, and then let's look at v.plot plus w.plot. Let's just see what it looks like. These numbers are terrible, so maybe this plot will look horrible. I don't know. Yeah, okay, not so horrible. So that's what the plot looks like. And we said that the inner product, we said it was negative. And from class, what does that mean? I think I may have just said acute a moment ago, but what that really means is that they're obtuse. And we can see from this figure that indeed these vectors are actually obtuse. So I misspoke a moment ago. Okay, cool. I hope that this is useful and sort of helps you sort of play around with some vectors and maybe helps give you some intuition for what these things look like.